Okay, so this is my extra credit opportunity lecture. It's going to be cover material over lesson 17 over the exam 3 material by Dr. Smith. So in lesson 17, we covered acid and bases. So to get us started, let's just go over what an acid is. An acid is a chemical substance that neutralizes alkalis, dissolves some metals, and turns litmus red. Typically, it's a corrosive or sour-tasting liquid of this kind, so I don't suggest putting it in your mouth at all, or you shouldn't be doing that at all, as Dr. Smith has said. A base is a chemical species that donates electrons, accepts protons, or releases hydroxide, also known as OH minus in its symbols, ions in an aqueous solution. So, these two are very important because this is going to be the foundation of exam 3, just knowing acids and bases. And so the next thing we got into was something called the Arrhenius model. Correct me if I'm saying that wrong. But it all starts with Svante August Arrhenius. In 1903, he received the Nobel Prize in chemistry for his electrolytic theory of dissociation, which states that molecules of acids, bases, and salts dissociate into ions when dissolved in water. I just feel like this is important to know because I really wasn't sure who this guy was, but looking into it, I now know, so I just wanted to include that in there. And so, like I said, we covered the Arrhenius model. This will define acids and bases in terms of how they affect the concentrations of hydrogen and hydroxide ions in an aqueous solution. So you're going to be seeing those two symbols a lot over the exam 3 material, so just make note of that. We then kind of jumped in to who Bronsted-Lowry is. So in 1923, a guy named Johannes Nicholas Bronsted and another guy, Thomas Martin Lowry, proposed a theory involving acid-base reaction theory. So this is where everything gets good. It's the fundamental concept in which an acid and a base react with each other. The acid forms its conjugate base and the base forms its conjugate acid by exchange of a proton. So the hydrogen, cation, and stuff like that. So I'm going to kind of scroll down now. And I'm sorry if this view is not very good. I have y'all on dog treats as my tripod, so... Okay, so we're going to talk now about a Bronsted-Lowry acid. Right here is where it's at. So it's good. I'm going to go ahead and try and highlight acid and then donates. And I'll tell you why in a minute. So a Bronsted-Lowry acid is able to donate a positive hydrogen ion, whereas a Bronsted-Lowry base is able to accept a positive hydrogen ion. Atom, not ion. I'm going to highlight base and accept. So, the reason why I did this is because it's an easy way for me to remember that an acid, in this case, is going to donate a positive hydrogen ion and that a base is going to accept. The reason is because I think of it as an acid donates and A and D. So, donate starts with a D. But with me learning disability, sometimes I switch a D to a B. So it kind of just helps me because we're talking about acid and base. So an acid is going to donate. So I don't know how, but this just helps. It's kind of like an opposite effect. And a base is going to accept it. So accept is not going to go with acid and base isn't going to go with donate. It's going to go vice versa. So if that helps anyone, I put that in there. It is confusing, but for me, it's just an easy way to understand. So, we're now going to go to problem 1 that I have here, where we're going to label whether the species is an acid or base or conjugate acid or base. So, in this problem, we have bicarbonate, which is the HCO3- aqueous, and then we also have a hydrogen fluoride substance. So to understand this better, we're looking to see who's going to be donating the hydrogen ion and who's going to be accepting it. So we know that the bicarbonate atom and the carbonic acid ion here. So basically these two that I have here are going to be a conjugate acid and base pair. This is because right here the H2CO3 aqueous solution is taking the hydrogen ion and it's going to give it to the bicarbonate ion, to the bicarbonate substance. So therefore it's going to make it the conjugate acid in this case, and the bicarbonate is going to be the base. So right here it's an acid, so it's going to be donating it, and this is going to be the base because it's accepting it. And that's going to be vice versa with the hydrogen fluoride and the fluoride ion here, because as you can see, this is going to be giving it to the fluoride ion. So it's the same thing. So right here, so this is known as the conjugate acid once more because it's going to be donating it to the bicarbonate right here. And I know it's a little tricky to understand with the conjugate acid and base, but I feel like that helps a lot knowing what an acid and base is. And it is also confusing because you might think it's opposite because there's more hydrogen ions in this one. But this is actually donating it right now to that. So that's going to make it a base. Bicarbonate is the base, and the carbonate is going to be the acid. So now we're going to kind of get more into conjugate acids and bases. And I was like, see, I forgot to bold that. So when an acid reacts and ends up losing a proton, then it's known as a conjugate base. Like I said previously, you can kind of see that in that example. And when a base reacts and gains a proton, it is then known as a conjugate acid. So these are good definitions to know. So I'm going to go ahead and bold that. So here we have another equation, and here we can see that the HCl and the Cl minus, those are going to be our acids, and these are going to be our bases. So this is just another quick example of how it is. I also went ahead and added in the common strong acids, especially that I'm using in this lecture. So we have hydrochloric acid, here's formula, hydrobromic acid, formula, and you kind of get the rest. I'm just going to kind of leave that in case you want to write it down or whatnot. But these are good to know, and these are good to memorize to know what is a strong acid. I didn't put in the base, I'm not sure why, but you can kind of figure it out as you go along. So I also got this chart from Khan Academy because that's also a great resource to understand a lot of this material as well, and I don't want to get copyrighted for that. So next we're going to talk about water. So it's important to know that with the water in acids and bases, it can be used as an acid and it can be used as a base, and therefore it is known as amphoteric. So that's just like it's both an acid and a base. When a substance can be used as both, it's amphoteric. So we're going to now discuss the equilibrium expression of water. So we're going to have KEQ equals H3O and then OH minus, because no liquids are in the equilibrium expression. So I just think you're going to use the KEQ a lot over the next couple lessons. So it's just important that we do this now. It's like I said, this lesson is the base of everything. So so it's going to be the hydronium ion, and it's going to be the hydronium ion, and it's going to be the hydroxide ion. And I'm sorry I keep stuttering. So now we're going to get into finding pH, and I just think this is so much fun. I don't know, I found it very easy, and I was kind of sad I missed this when I went to Arizona, so I'm excited to get to kind of cover it myself. So pH is equal to the negative log of the hydronium ion. So that is the equation, that is the formula that you are going to have to memorize. So it's important to go ahead and highlight this. And then we also need to know that the hydronium ion is equal to the hydrogen ion. So for an example problem of this, we're going to find the pH of a 0.0025 molar hydrochloric acid solution. The HCl is a strong acid and is 100% ionized in water. The hydronium ion concentration is, like I said, 0.0025 molar. So to do this, we're going to take the formula from above that we have highlighted, so pH equals the negative log, and the hydronium ion is going to be the 0.0025 molar HCl solution. So then it's kind of like a simple plug and chug, so you can do this on your calculator, just type in the negative log of that, and then you're going to get 2.60 straight. It's just going to be just like that. In my work, I just did the log of 0.0025, and then I got negative 2.60, and then I have to add in the negative, which two negatives makes a positive, so that's how I got it positive. So now we're going to be discussing the POH, and POH is the negative log of the hydroxide ion. It's also, this is another formula you must know over the course of the material. And we're also going to get the pH plus the POH is equal to 14. And this is a very important equation to know and have memorized, because this is an equation that you're going to flip around and you're going to be able to solve for POH and pH during the course of the material again. So the problem, this is our last problem, this is the last thing we're discussing right now. We're going to find the pH of a chemical solution if the hydroxide ion concentration is 4.22 times 10 to the negative 5 molar. So we're going to start off with the POH formula, which is the negative log of the hydroxide ion. And so the 4.22 times 10 to the negative 5 molar is going to be the hydroxide ion. So we're going to take the negative log of 4.22 times 10 to the negative 5, plug that in, and we are going to get 4.37. So I highlighted that because that is our answer for the POH. Then, like I said, we're going to come back up here and we're going to use this formula right here, pH plus POH equals 14, and we're going to rearrange this to get the formula pH equals 14 minus POH. So then with that, we're going to solve for pH. So we're going to use 14 minus the POH that we found, which is 4.37, and we're going to get a pH of 9.63. So that is all of the material we covered in lesson 17, and I hope this was very helpful and I had a lot of fun doing this. So thank you.